Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to look at the Crank-Nicolson method for approximating solutions to partial differential equations, and we're also going to look at insulated boundary conditions. So this lab is going to look both at solutions to the heat conduction diffusion equation using the Crank-Nicolson method as approximating those solutions. This is an implicit method, unlike the previous method we saw in Lab 2, which was explicitly defined. We'll review this. However, we're still going to use the same math that we used both in Lab 1 and Lab 2. So there isn't really all that much new here. What's significant, however, is this method is unconditionally stable. Previously, with the last finite difference equation we saw in Lab 2, it was only stable conditional on kappa delta t over h squared being less than 0.5. Now, once we've looked at the Crank-Nicolson method, we will then define the characteristics of insulated boundaries and how we can approximate them. We will then implement insulated boundaries into the Crank-Nicolson method. Now, by the end of this lab, you will understand the Crank-Nicolson method, and you will understand the definition and how to approximate insulated boundaries. Now, as a review, going back to Lab 1, what did we do? We were approximating boundary value problems. We took the linear ODE and we converted the linear ODE into a finite difference equation. Now, by substituting in specific values, we found that we could write down the finite difference equation as a function of three unknowns and a known forcing value. Now, we had to write down this equation for each of the interior points. So this gave us n-2 linear equations that had to be solved. Now, in fact, there's n unknowns, but the boundary conditions gave us u sub 1 and u sub n. So this gave us a system of linear equations which we solved, which approximated the solution to the boundary value, actual solution to the boundary value problem. Now, in Lab 2, we used an explicit method. Now, here we found this finite difference equation. Now, this finite difference equation approximated a point in the future by using three known values. And those three known values were from previous time. So we stepped forward and explicitly calculated the unknown at the next step in time. Now, all the values on the right-hand side are known. And we knew all the values at time t sub k. So all we had to do was approximate the solutions at each of the interior points at the next time. Now, how did we get this finite difference equation? This finite difference equation is found by taking these two approximations of the derivative using these 2 points and the concavity with respect to space at these 3 points, and we substitute those into the heat conduction diffusion equation. Both of these two equations approximated or focused on this particular point at space x sub I and time t sub k. Now, what happens if we focus instead at the point in the future, the unknown point at the future? Well, we can still find approximations of the rate of change over time and the concavity at that point, and then both of these focus at this point. If we substitute those back into the heat conduction diffusion equation, we get a very similar equation. However, now we're dealing with 3 points that are unknown. There's only one known, u sub ik, and there's 3 unknowns that we have to solve for. Now let's compare the two methods. Here we're using 3 points that are known to calculate 1 point in the future. Here we're using 1 point that is known to write down an equation that involves 3 points in the future. The equations themselves, however, are very similar. The only difference is these 3 points are at time tk, these 3 points are at time tk plus 1. Now, beyond the scope of this course, however, the appropriate thing to do at this point is simply to add the two equations. So if you have two equations that are true, then the sum of those equations are also true. So we could use different proportions, but for simplicity, and actually we'll see later for correctness, all we have to do is add these two equations. So this is the heat conduction diffusion equation focusing at this point. This is the heat conduction equation focusing at that point. Adding the two together gives us a much larger equation. Now, it's getting a little bit messy, so let's let the ratio R be kappa delta T over H squared. That simplifies the problem. And now let's simplify and collect. So let's bring all unknowns to the left and all known values will be sent to the right-hand side of the equation. So now we have a new finite difference equation that involves both 3 unknowns and 3 known values. Now, just like we did in lab 1, yes, we could just write down n sub x minus 2 equations, and at each of the interior points, x sub 2 to x sub n sub x minus 1. This gives us n sub x minus 2 equations and unknowns. And again, there are 2 n sub x unknowns, however, the boundary conditions will give us those 2 particular values. So if we know these values, we know that this value is just the boundary condition at the left-hand side at time t sub k plus 1. This boundary condition is just the boundary condition at the right-hand side also at time t sub 1. So let's bring both of those values to the right-hand side of known values. So now we have n sub x minus 2 linear equations and n sub x minus 2 unknowns. We can take this just like we did in lab 1 and write it in matrix form, mx equals b. Here's our matrix. Just like in lab 1, it's quite regular. Here are our n sub x minus 2 unknowns. And now here we have a much more complex right-hand vector of known values. Now, fortunately, the right-hand vector actually has a lot of structure which you can exploit. So you can see that it's just twice the value of the previous interior points, plus r times, or ratio, times, oh, that looks a lot like something that we got from diff. We can calculate that as well, and we now only have to update the first and last entries as well. Now, given an initial state at time t1, all we have to do is create a system with the appropriate number of equations at time t2, and then solve for the unknown points. We would essentially create the system of equations, solve it, and substitute the values back into the matrix U. Now, given these values, we can set up another system of n sub x minus 2 equations and unknowns, solve them, and substitute those back into the matrix U. And we can carry on until we get up to time t sub n sub t. Now, the signature of this function is almost identical to the signature for the diffusion 1D. However, it will be the Crank-Nicolson 1D function. Everything else is the same. Again, kappa is the diffusivity coefficient. X sub range is the spatial range from A to B. Nx is the number of points into which we will divide the range AB. T sub range is the time interval from t naught, our initial time, to our final time, t sub final. Nt is the number of points in which we will divide time into. U init is a function handle giving us the initial state. So what is the state of the system at time t naught? And U boundary will return a pair of values for any time, and those pair of values will be the boundary conditions at both A and B. Now, when we're implementing this function, we don't actually have to worry about error checking at this point because we no longer have a catastrophic problem if kappa delta t over h squared is greater than 0. The Crank-Nicolson method is unconditionally stable. There are no values for which the solution or the approximation will diverge. Nonetheless, if this ratio is greater than 0.5, there may be decaying oscillations in the solution. So it's still a problem if the ratio is greater than 0.5, but it's not a serious problem, or at least not as serious as with the explicit method we used last week. So instead of issuing or throwing an exception, we will simply issue a warning. By issuing a warning, we will say, hey, certain particular arguments are suboptimal. This is the general structure. Now, the warning will be seen by the user, but unlike an exception, this will not terminate the execution of the function. The function will happily carry on executing. Now, we have to initialize u, and we have to initialize the appropriate values, just like we did last time. So a lot of that's a repeat. It's the interior values that we have to calculate from time t2 to time t sub n sub t. So for each of the points in time, for k going from 2 to n sub t, we will have to do a little bit more, however. Unlike the previous step, where we just had to evaluate all of them, now we actually have to set up a system of linear equations, solve that system of linear equations, and assign those solutions to the interior points in the appropriate column of the solution matrix U. Now, there are no real MATLAB commands that you need for the Crank-Nicolson method that you haven't already seen in labs 1 and 2. So, consider the following. The initial temperature of a bar is 1 degree Celsius. The bar is placed in contact with two barriers. One is at negative 1 degree Celsius, the other is at 2 degrees Celsius. Now, the initial state is just a function that always returns a vector of zeros or a vector of ones for any number of vectors in the argument. The second function, the boundary conditions, this one will return a row of ones. This will return a row of twos, a row of negative ones and a row of twos. Now, if we plug these into the Crank-Nicolson method and call mesh, you will notice that, yes, we get a convergence, and it's going to the solution to the Laplace's equation, a straight line. Here, kappa delta t over h squared is approximately 2. Now, if I change the values, get a few more points, now this ratio is 240, significantly larger than 0.5. It still seems to be converging. However, you will still notice that there are oscillations in the solution. So it's not converging smoothly. Even if we increase the points, here we have 60, the ratio is 60. Again, there's more points in time, but again, we see an oscillation. Using values of n sub x and n sub t so that the ratio is 1, it appears to be significantly smoother. Now, let's consider an alternate example. The initial temperature of the bar is 0 degrees and the barriers are 1 and 4. Here are our boundary value, or our initial function, our initial conditions and our boundary conditions. And now we start at a temperature 0, but now both ends begin to increase. Now, if we take this output and put it through the functions animate, and then take the frames that come out of that and pass it to frames to GIF, we get the following GIF, which is an animation of the progression of the temperature along the bar as time increases. If we increase the number of points, again, it looks a lot smoother. However, at the same time, we can also see in the animated GIF, again, it's converging quite smoothly and quite nicely to the solution to Laplace's equation. That's a straight line going from this point to that point. The greater the concavity, the greater the rate of change. The less the concavity, the less the rate of change. Now, that's it for the Crank-Nicolson method. So now we're also going to add something else onto that. We're going to look at insulated boundary conditions, because up until now we've only looked at conditions where the values at both endpoints for all values of time are fixed values. Now they may change over time, but they are still fixed values. Those are Dirichlet conditions. Another possibility is to specify not the exact values at the boundaries, but to specify the derivatives at the boundaries. These are known as Neumann conditions. However, we're going to simplify life a little bit by looking only at one specific case of Neumann conditions, and that's insulated boundary conditions. So what happens if you place a bar in contact with a body of heat, providing heat, but you insulate the other end? So we've looked at boundary conditions. Now we're going to look at Neumann conditions, specifically focusing on insulated boundary conditions. So suppose I have a bar here that's at 100 degrees Celsius. Now, the entire bar is at 100 degrees Celsius, and then let's say at time t naught, or t equals 0, we're going to take one end of the bar and put it in contact with a heat sink that's at 0 Celsius. Now what's going to start happening? This end here is still going to be insulated. Now over time the bar is going to cool. First it's going to cool over here, and over time we expect the cooling to propagate throughout the bar. So at some point the other end of the bar is also going to start cooling, until ultimately we're going to go to the solution to the Laplace's equation, which is essentially 0 degrees Celsius across the entire bar. Now, what does it say mathematically to say that a boundary is insulated? Well, a boundary is insulated if, given a particular point t sub k, or in this case t sub k plus 1, the boundary A, or the left-hand endpoint, is insulated if the rate of change with respect to x is 0. So there is no change as you're approaching the bar, as you're approaching the insulated barrier. So let's say you had an insulated wall and you were bringing your hand closer and closer to the wall. Now, you would not expect it to get either hotter or colder if it's an insulated boundary condition. On the other hand, if this was heated or cooled, as you were approaching, you would expect it to get either hotter or colder, respectively, as you were approaching it. But with an insulated boundary condition, we don't expect any change in the temperature as we're getting closer and closer to that boundary. So essentially, the derivative with respect to space at the boundary, if it's insulated, is 0. Now, we could use the following order h approximations of the derivative at these endpoints. So this is the forward divided difference formula, while at b we have to use the backwards divided difference formula. We're going back in space because we can only go back into the interior of the interval AB. However, these are order h methods, and when we were approximating the second derivative, we were using an order h squared method. So let's use both forward and backwards divided difference formulas for approximating the first derivative, but let's use the order h squared approximations. And so now we have two terms. We're looking at a plus h, and a plus 2h. So 2 points into the interval. Same at b minus h, and b minus 2h. We're looking at 2 points back into the interval. So if the boundary condition for an insulated case is that the derivative is 0, this essentially says that this ratio is 0 and this divided difference approximation is 0. Now, let's multiply both sides by 2h and substitute our approximate values at each of these points into those equations. Now, next step is, just like previously, we had to have some information about the endpoint. With Dirichlet boundary conditions, we were given the values at the endpoints. However, now let's solve for this value and let's solve for this value. Those are the endpoints. Solving for them, we get these two values. So now this value is some linear combination of the next 2 points. the other endpoint at B is a linear combination of the two previous points. Now, the first and last equations are here for our finite difference equation. Now, previously, for the Dirichlet condition, those two values were known, and we just brought them to the right-hand side. However, now they're insulated, and so they're unknown, because these two values now depend on other unknown values. So I'm going to approximate my value of one endpoint, and this depends on u2 k plus 1 and u3 k plus 1. And over here, I'm going to do the same. Those two substitutions are made, and now I have a slightly different equation. Now the first term here is slightly different from the normal value. The second term here is also slightly different, but now we are not changing the right-hand side. There were no extra terms added here, at least if both sides are insulated. So recall previously here was our matrix M, and it was quite regular. If the left-hand endpoint is an insulated boundary condition, we're no longer changing the vector, but rather we are now changing these two values in the matrix. Similarly, if the right-hand endpoint B is insulated, we will change these last two values, and we will not be changing the vector B. Now, how are we going to indicate an insulated boundary condition? Well, one of the nicest ideas I had was we can specify an insulated boundary condition with a special value. The boundary value function will simply return not a number. Now recall that not a number is the result of floating point operations such as 0 divided by 0. If you calculate 0 over 0, it's indeterminate, it's not a number. This is also sort of appropriate because an insulated boundary condition isn't really defined. It's not an undefined temperature. It depends on the temperature around it. So now, if we had a right-hand endpoint that was insulated, then the first column would be, say, 1.7 degrees, or sorry, the first row would be 1.7, the second row would be all not a number. Now, one problem. IEEE 754 specifically states that if you try to check, is not a number equal to not a number? Guess what? They're not. In fact, if you ask, is this not a number not equal to that not a number? The answer is yes, they are not equal. This is a requirement in the standard. So how do we fix this? There's actually a function called isNotAnumber, and you can pass it an argument, and if the argument is not a number, it returns 1. So here's our matrix. Here we have an initial condition where everything is 1. Our right boundary condition is a constant temperature 2, and the left boundary condition is a temperature 1. Now, for these specific values, if you plug that in with the two previous functions, you would create a system of 4 equations and unknowns, and when you solved it, you would get these 4 values. Those 4 values would be substituted into the matrix. Now we still have this interesting boundary condition. Well, right at that boundary, we can calculate the temperature again by just using the approximation we used. 4/3 times this value minus 1/3 this value gives us our approximation right at the boundary. So we've calculated that, and now we go on to the next step. We have to calculate the next 4 values. All these values are known, these values are unknown. So now again, we create a system of 4 equations and unknowns. We solve that system of equations, we get a new set of values. We can substitute those back into the matrix. Again, we notice that it's heating up quite quickly at the right-hand side. Over here, it's heating up much more slowly. We can then again copy, take 4/3 times that value, minus 1/3 that value, and that gives us the second boundary conditions. We would repeat this over and over again for each time step t sub k k going from 2 to n sub t. Now, if the boundary condition was at the point B, or at the right-hand endpoint as opposed to the left-hand endpoint, then rather than using the first two values, we would use the last two calculated values to approximate that entry. Now, solving. We only need two small changes. First, now that we definitely need two interior values, we must make sure that n sub x is greater than or equal to 4. Second, it's actually not that much additional work. For each time step from 2 to n sub t, we'll have to make a few slight changes. We'll set up the system of linear equations, but now it's a question. If we have a Dirichlet boundary condition, then we update the vector. If we have an insulated boundary condition, which we check by using not a number, then we have to update the matrix. Then we just solve the system and substitute those n sub x minus 2 values back into the solution matrix U into the appropriate column. There's only one last thing we have to check. If one of the endpoints, or both, were insulated, then we have to use a linear combination of the next two interior points to approximate the value right at that insulated boundary. So ultimately we're going to get an image that looks something like this. Again, very quickly it heats up over here. We have very fast heating over here. However, at the insulated boundary condition, it only begins to heat up very slowly. Increasing the number of points, we get a little bit finer gradations. And again, just like previously, we can take the output of the matrix of the function, we can pass it and create an animation, which is then saved, in this case, to another GIF. And as we can see, temperature very quickly heats up to 2 degrees, and slowly, more slowly, the rest of the bar begins to heat up. The less the concavity, the straighter the line, the slower the increase in heat is. Again, that's just a consequence of the heat conduction diffusion equation. So, we've looked at the heat conduction diffusion equation. We've developed the Crank-Nicolson method. You're going to have to implement this algorithm. Unlike the previous implementation, there's less restrictions on the ratio kappa delta t over h squared. If it's greater than 0.5, there may be transient oscillations, but we still get convergence. It's unconditionally convergent. We then defined insulated boundary conditions, and we considered how to implement these how to approximate such insulated boundary conditions in MATLAB in our systems of linear equations. Thank you very much. Have a good evening.